Okay, thank you very much. So I want to first thank the organizers for really the wonderful organization, which every time I come to a GSI, Frederick, you surprise me because you do even better thing. This time the Senna, the Seine trip with the boat. So it's wonderful. It's really, thank you for all the great organization. And today we'll speak about this work, Thermodynamic Interpretation of the Learning System, which is a joint work with Francesco Faglioni and then two students, Morri and Squadrani, that have helped us with the calculation. I want to be clear that it contains very little mathematics and is purely experimental. And we try to test some hypotheses, and we will show you what has happened when we try to test common hypotheses. So first of all, I just wanted to keep this talk self-contained. I'm aware that practically all of us know what a deep learning system is, but what is the task? So this algorithm is for classification of typically images, but not only, of course. You have a certain data set, and then you have the algorithm to classify it. That usually consists of a series of convolution layers, and then there is a max pool layer, and then in the end you have a few linear layers, and you get an output. Okay, so it is what you need to know is that this algorithm is a sequence of layers of different types, and then when you do the deep learning, so-called algorithm, you do three phases: the training, the validation, and the test. Well, in the training, essentially, you're fixing some hyperparameters, and then you test on your validation set, and you discover what are the best hyperparameters. Typically, is the shape of your algorithm, but there are well-known. Now you don't have many freedom. People have worked out very clearly what these hyperparameters are. Okay. Then there is something very important called the score function. The score function is a vector. For example, here it is n components. If the output is 4 classes, this n is equal to 4. So it contains as many classes as what you want to classify. And then this is the loss function. I've heard many talks today and yesterday about loss function. You all know what that is. But essentially it measures the error between the predicted label of some data and the correct label. Here I write the cross entropy just to fix the ideas. It doesn't have to be the cross entropy. It's just some black box that measures the difference. Now, this is the loss for one data. In my case, it was an image, but it doesn't have to be. And here is the total loss. So you're measuring the error that you get after you see what is the correct labels versus the predicted one. And then the optimizer, it's a very important ingredient because then at each iteration, you change the parameters to reduce this loss function. Okay, so this is like 2 minutes on the deep learning algorithm. Now, if we look at the training set, we call it K and the loss function. Now, we take the gradient, and the typical gradient descent step is that you move at the time t plus 1, so it's discrete, of course, you move according to the gradient. So you go down, you want to minimize your loss, except that in deep learning, you use the stochastic gradient descent, which adds some noise to this procedure. And we speak presently on what I mean with this word. The two hyperparameters that occur the most is the learning rate, which you denote by eta, and the mini batch size. And so you can play with those, and there are actually some recipes with which you can play to see how you improve your accuracy if you change this. Okay, so that's the game that people have been playing, the game that we play also. Now, I just wanted to put with this slide the fact that if you have a gradient descent, you reach a point where the gradient is 0. Well, of course, because you go down. But if you take the stochastic gradient, it is well known that you don't reach a point where the gradient is 0. And so you are not reaching the critical points of the loss function. I mean, this is easily verifiable, right? Because you look at the equilibrium point, you check the model when it reaches a great accuracy, you look at it and you discover that it's not a point with, in fact, this is a picture where you show the eigenvalues at the critical point, a stopping point, they're not all zero. This is well known. I just wanted to tell you, just to realize that your system doesn't reach a point and stops. No, that's not how it works. Okay, now I briefly discuss the work we start from. Chaudhary and Soato, this is a work in 2017 that got me interested in this business. Before that day, I didn't know what was artificial intelligence, so I'm now disclosing the fact that I'm like infiltrated. I'm a mathematician trying to understand this business. I'm not a computer scientist. So Chaudhary and Soato, I talked to them. They're also my co-authors. When I wrote this paper, so they explained to me they substitute this discrete equation with the continuous equivalent. And as well as we realized that this passage, I realized with this conference, is not so obvious as it might be, right? But this is what everybody does. Simply translate this to a differential equation. And what Chaudhary and Soato do in their work, they simulated the stochastic descent with this differential equation. I'll come to it in a moment. This is an instance of the Fokker-Planck equation. I think the previous talk was concerned about some very clever and refined way to discuss it. Now, dW is the Brownian motion, so it is a stochastic process that is totally isotropic. So in order to take into account there is an isotropy in the system, you need something called the diffusion matrix. I will say something about it, but it was appearing also in the previous talk. B is the mini batch, so the parameter eta, which is the learning rate, and the size of the mini batch, this quotient is taken as temperature. So they translate to thermodynamic temperature. That's what they do in this work. They continue, they wrote more than one. So they really insist on this point. Now, I want to convince you that it makes sense what they do, because if you have a very low learning rate, it means that you're moving very slowly. So you don't have much, your system is not agitated because you move slowly. And if the mini batch is very big, then again, you are doing not the stochastic, but the gradient descent. So in some sense, these are two instances where the temperature goes to zero, so to speak. So your system is not stochastic, it's deterministic. So they have this interpretation, but then being a mathematician, I don't like when they don't explain things to me, so I try to understand them. So what they do, they use the Fokker-Planck equation in the ethos approach, which is a stochastic equation. As I said, is the diffusion matrix which gives anisotropy of the system. And I also worked out in a paper with them more about the meaning of the diffusion matrix. So Einstein was mentioned in the previous talk. I took Einstein approach. I don't want to speak about this because this is actually more mathematical and more fun for mathematicians. So, but I wrote a paper with them I referred to about this diffusion, but it's not today's talk. What is important is that in the end, they obtain a steady state by solving this ethos equation, where they get, just this is a normalizing factor. They got the steady state in terms of phi. So they've replaced the loss function with this potential phi and interpret the temperature as this. Of course, you recognize for sure, the Boltzmann equation, this is clearly expressed. There is a constant here I didn't put because, of course, you can absorb it somewhere else. But this is the consequence, the ideas that were developed by them. Then they also observe, and again, this was in the previous talk, that there is something called J, which is the current, that is expressed in terms of the diffusion matrix. And this measures how the trajectories of SGD are influenced by the anisotropy. And they show that for a very large value, you get this periodic trajectory, while if you have J small, you go to a point. Now, we take this, like we say, okay, let's see what happens. And what we did, we tried to take a thermodynamic analogy. So this is what they do, actually. So it's not our idea. But we tried to take a thermodynamic analogy, really, to say, okay, thermodynamics has also global as global quantities. So we look at discrete picture here, we look at the continuous picture, and the parameter of our model, the weights, right? We interpret them, each weight is a particle in one dimension. So we have a trajectory, and we have a kinetic energy, and we relate the kinetic energy with the temperature and see what happens, because that's what it should be. So we're essentially trying to do what Boltzmann was doing, but of course we're not Boltzmann, so it's so we have an instantaneous kinetic energy, we have an instantaneous temperature, and then when we're near the equilibrium, we can compute average of both, and of course they are related by some constant. Now here we got a choice, right? So what we had to do, we had to decide whether our particles had all the same mass, or if we decide to go with the particle with the same mass, it turns out that each layer has a different temperature. So this is something surprising to us. Because if the system is at equilibrium, it makes no sense to have different temperature at different spots, right? Either that, or you decide that masses of different layers are different. This is another possibility. Same temperature everywhere, but different masses. So this is a first choice that you have to make about this fact. We decided conventionally to set the masses equal to 1, and then get a different temperature. And then we look at this very simple equation, and we look at Newton's law, and we discover something that I've been hearing a lot these 2 days, right? That our system, notice, this is the system how we should evolve according to Newton's law. This is the system that we actually have. And if you compare the two, you see that the temperature is set equal to 0 at each step. So essentially, you're extracting heat from your system. And while the gradient descent leads to a local minimum of the potential, the stochastic maintains the residual final temperature. That is, so we don't achieve the minimum of the potential energy, but we achieve the minimum of the free energy, which is the Legendre transform of the potential energy, right? So we're getting a different system than one may think, and we need a dissipative term. So after we made all this observation, we tried to see what happens in a concrete example, and we did the experiment with MNIST. So we did 2 sets of experiments, one with MNIST, one with CIFAR. Both get the same results. So I'm expressing the one in MNIST because I didn't want to express, I don't want to give you too many graphs, but they're really the same. So we take a small MNIST because we have to follow the parameters, so we don't want a small Lennett because otherwise the parameters of MNIST get too large. We want very few parameters. Anyway, you get very good accuracy. So we let the model evolve, monitor temperature, we define it above, and we measure the temperature at equilibrium. Okay, so that's what we'll be doing. So I told you it's an experimental talk. We don't find any theorem, we find experiments, and they're all negative. So we have the layer reach some equilibrium, okay, after 30,000 epochs, some earlier, some not. And the system keeps evolving. So even when we reach equilibrium, somehow the system keeps moving, but that we know. Everyone knows the parameters keep moving. I show you a picture where you see the movement of the parameter, but before that, we look at the temperature and learning rate. Now, the temperature should depend linearly from the learning rate, and it doesn't look linear at all. So it actually looks different for each layer, convolutional and linear. So this proves that what people, not just Chaudhary, but many people have been doing, it's not really how it should be. And the same for the batch size. See, the batch size should, again, 1 over the batch size should be linear, but no, it's not. And we see that too by changing. And then I want to show you this parameter versus mass or temperature, because it's a convention. And this is something that Professor Welling was also alerting me. Notice there are some layers where the parameters are fixed, they don't change, and some layers where they change a lot. Somehow there are parameters that don't matter. So it felt to us that you can get rid of those somehow, right? This is something that we've been really thinking about, symmetries, stuff. It clearly shows you after 30,000 epochs what you should do. Now, how can we model this behavior? Now, first of all, we need to modify the Fokker-Planck approach because you can't put a T as they did, definitely. So the equation that and in fact, they get this J very complicated. There must be something else. Contact Hamiltonian, totally, yes, that's what one should do. Should use this equation. You should do entropy. We could measure entropy, right, and check if everything works with this approach. And then Lie Group Thermodynamics, of course, there are symmetries in the particles. It's clear from the graphs. We should be able to exploit them. We didn't do, as I told you, this is a negative talk where we say things that are thought to be true, they're not. And finally, my conclusions, I have 1 minute, right? Yes. So the conclusion is that temperature near each layer behave independently. MNIST and CIFAR are totally same. There is no dependence linear as people think. The system is dissipative for sure. It's not mechanical because the Hamiltonian mechanic, no. And we hope that the insight from Lie Group Thermodynamics and contact Hamiltonian dynamics can help us in understanding more this picture. In the end, I just want to give you the bibliography that helped me greatly, and I thank you for your attention. Thank you very much.
Thank you very much. So, is there any question?
Yes.
No?
Just one.
Okay.
You've read the talk. So there is a whole literature which is about stochastic gradient MCMC. Do you know about that?
Monte Carlo, you mean?
Yeah, Markov chain Monte Carlo.
Yeah, I'm working on that too. Yes, indeed. Monte Carlo is very exciting. Yes, yes.
But that's also learning. But then and so there you see the phenomenon very clear. They have an explicit temperature, and it's quite clear that when you're sampling from the posterior, you're sampling at temperature 1, right? And so all these things are very. And there's this when you do it on stochastic gradients, you can show there's Hamiltonian versions of this, there's thermostats of this.
Yes, I'm glad you asked this question. I'm doing it with some other people, but I was not aware that there was Monte Carlo in deep learning. That I was not aware. Are they doing deep learning?
Yeah, you can apply these things to deep learning, no problem.
Because I've been doing Monte Carlo with different things, not applied to this deep learning.
Sort of doesn't matter whether you apply it to. It's just a system with parameters, and you're trying to compute the posterior distribution, the Bayesian posterior over the parameters. Whether that's a neural net or not, it doesn't matter.
Yes, yes. No, but thank you for the feedback. Thank you very much.